quantum mechanical model builds on the Bohr model, where we know that we have a positive nucleus and negative electrons, and those electrons have particular energy levels. They don't just go anywhere and have any energy level. They have set energy levels. But still the Bohr model didn't work, and it took Schrodinger and a few other guys to come up with a new model. And the main difference between this model and the old model is that they treat the electrons as standing waves. In the Bohr model, they had circular orbits. They were it was like a solar system model, basically. But this time they're treating them as standing waves. So when the standing wave, let's say, is going around in a circle, that circle would only have certain energy levels that would fit into that, because if it has too little energy or too much energy, then these waves would interfere destructively, is basically what would happen. So let's say I have n is equal to 4, so 1, 2, 3, 4 nodes, crests, so 4 wavelengths. I could change it to where there is a whole number of 5, but I can't have 4.5, because then they would interfere destructively. It's like, if anyone has ever played with like a jump rope or some rope where they've been just swinging it with 2 people, just up and down, not for jumping over, but just acting like an idiot and just swinging around like when you're a kid or something like that. When you do that, both people have to do it with a certain force. Otherwise, when you do it right, you get something that looks kind of like this. That's why people used to do it, because it was fun. And you would get something that looks like this, or a different little, or you might even get one with 3, like this. And when you spin it really fast, then it looks like there are a bunch of little loops in there. But if one person decides to change their end, or if they go a little bit too slow or too fast, then this whole thing destructs, basically. It'll just blah blah blah. It just goes away. So that's why there are only certain energy levels that will be allowed if it had some kind of set orbit. So with this idea in mind, Schrodinger went ahead and came up with some equations to describe those orbitals. So these are called the Schrodinger equations. It's a lot of linear algebra, and honestly it's just not really that important. This is the operator, this is the total energy. It's just not important right now, to be honest. That's another thing when learning about this. It's just really just try to, especially for a general chemistry class, really just try to take on board the main points. It's not that these aren't interesting and that they are not useful to know, but every single time you have a question and I were to answer that, it would raise like 10 more questions. You'd be even more confused. So at this point, really, it's just best to keep it as simple as possible. The main points are here is that energy acts like not energy, well, maybe energy to some extent as well, but the electrons, when they're in these orbitals, they act like waves and not really so much like particles. And the next part is going to be about the orbitals, which I'm about to get to. So back to what I was talking about. We had kind of the Bohr model. It was acting like particles, and these little circular orbits. Obviously, it's not happening. Treat the electron like a wave. Okay. So Schrodinger came up with these equations, and the solutions to these equations give the different orbitals. It gives certain energies for these orbitals, and they have different numbers and names, and that will be gone into later. But the solutions to these equations give the orbitals, and before I can talk about the orbitals, I have to talk about one more thing, and that is the uncertainty principle. And the uncertainty principle says basically that we cannot know the position and the momentum of an electron at any given moment in time. And why, you might ask? Well, if you manage to come up with a way to track something that small and be able to accurately give its position and its momentum at the same time, then you'll win the Nobel Prize. You don't really need to go to school anymore. But until then, we don't really know we don't know really where an electron is going. So the orbital is going to be different in the quantum mechanical model than it was in the Bohr model. The Bohr model, we know where the electron is. It's going to go around in a circle. In the quantum mechanical model, we have no idea of how the electron is traveling. So what is this orbital then if it's not telling me where it's going and where it is? Well, it is telling me where it is to some extent. What these orbitals do is they give me a three-dimensional picture. This is in X and Y and Z. So it's in 3 dimensions. So if you take vector calculus or something, you'll be accustomed to seeing things in 3 dimensions. But anyways, it gives a shape, and what this shape tells me, and what this kind of density map tells me is the probability of an electron being found in that location. So an electron more often is going to be, at least for the 1s, as I forgot to mention, this is the 1s orbital. What that means I'll go into later on in quantum numbers and things like that. But this is basically a sphere shape, and the further I go in to a certain point, unless I approach very closely to the nucleus, this part is going to be, if I had it color-coded, would be very dark, because there's a higher probability of an electron being found there. And the further I go away, the less, if I were to do color, then the lighter it would get, and the less likely I'll find an electron. Now, what's important to remember about these orbitals is it does not tell me anything about the position. We have no idea what's going on in that orbital. They could be orbiting in circuits. It could be spelling out swear words. No one really knows. But also, these orbitals, while it looks like it has a defined shape, really doesn't. What this is, what generally people represent as the picture, quote-unquote, of the orbital, is the area where there's a 90% likelihood that I'm going to find an electron. But technically, the orbitals have basically infinite space. What happens is just the probability drops off to just something infinitesimally small when I get any significant radius. So we generally tend to ignore those because well, eventually, sometimes you do get strange scientists that, well, they're not really strange. It's just like making stuff up. I don't know. It's not really making stuff up. They're taking just, whatever. It's not really that important at this point. But just know there's a lot of nonsense in quantum mechanics. Often, there'll be an abysmally small chance of something happening, but yet, that it is a possibility, and whatever. It's not important. What's important is just, it's not the shape, and when it tells me that there is, let's say I find that there is a 90% chance at this point, or a 99% chance an electron will be there at that point, it doesn't mean that it's like stopped in time there. It could be working just like this. We just don't know. That's the whole point. So what's a little bit confusing is that we end up talking of electrons kind of like one of these standing waves. Like, well, if it's a standing wave, then why am I acting here like it's like a particle at a particular point? Well, it's just the math language. A lot of times in quantum mechanics, it's not very easy to visualize because you're almost talking. A lot of times you almost end up talking like apples and oranges, but sometimes it's just it's something that's necessary because that's just the only way we have best to express it. So sometimes you've got to, especially in general chemistry where it's just not that important to you per se, just not pay attention to it too much. What's important about the orbitals is going to become later when we talk about bonding, where you get overlapping orbitals. And really what's just important is just that that's just the area that it is most likely to be. We have no idea how it is traveling. It could be traveling in triangles, could be traveling in circles, could be, whatever. It doesn't matter. But that's the idea. And the most important idea of this really is just that the electron acts like a standing wave, and this also will be important with bonding. because a lot of times we're going to be able to tell if a bond will or will not take place due to constructive or destructive interference. So that's mainly the most important. That's why people discuss this kind of stuff. Because when we're talking about bonding, we end up having to take this kind of stuff somewhat into account a little bit, just to know the basic ideas, like it acts like a wave. That's really the most important part. Just because of it's, especially like in organic chemistry, just because some of these things are so small. I mean, a hydrogen atom really isn't very big, so a lot of these quantum effects, they will mean something at this level, even though it's still quite large compared to something a quantum physicist would be talking about. The parts of protons and leptons and all kinds of other kinds of things that just aren't important. But that's really all that really should be taken away from here. Electrons act like waves. They can, and because of that, there's going to be constructive and destructive interference. That's going to affect how it can bond with other elements or with other, just other things. How electrons are going to interact with each other, and then they interact inside of these orbitals, and these orbitals also will have a small part of how these electrons bond as well. Mainly not so much in general chemistry, but in organic chemistry later on, just the shape of the orbital. Sometimes it will be hard for a bond to take place, not necessarily because it wouldn't happen if it could, but just the shape of it, it might be blocked off by other stuff. So these are the two main things that are important. And if there are other questions that pop up because of it, it's not that I don't want to answer them. I do have answers to quite a lot of them. I always wanted to be a physicist when I was a kid, but so I did end up learning about a lot of this stuff. But every time you answer a question like this, it's just going to lead to even more questions. So I'm sure this probably seems like a bit of a letdown, but for a general chemistry class, it's just really hard to try. You want to answer the questions, and you do want to know more about it, but it's just not related to the class. And if I encourage you to definitely learn more about it, definitely to know a little bit extra sometimes does help. You'll see some things like organic chemistry, and you'll say, oh, I know that can't take place because of this and the bonding, and so it is useful. But just try not to go too crazy. It's just sometimes you try to make too much. It's not like you're trying to make too much sense of it. It's just they leave a lot out on purpose because it's just you'll end up getting sidetracked forever and forever, and you'll just keep getting more and more and more questions, and before you know it, you'll be a theoretical physicist before, and even then now you're a theoretical physicist and you still have no idea what's going on. So it's that's how it's set up. So I hope that it gives a good idea of like what you should take away from something like this in a general chemistry class.